Hi, Physics 100 students, it's Dr. Ricardo. We're going to go through the Chapter 5 notes, which are on fossil fuels. So, 85% of the commercial energy resources used in the world come from fossil fuels. And there are three kinds of fossil fuels. There's coal, natural gas, and petroleum. Coal is derived primarily from plant material that was buried um, in the earth millions of years ago and has slowly metamorphosed into this material that we call coal. So there's going to be three different kinds of coal that we're going to talk about, and it's going to depend upon the hardness of the coal. Um, and the harder the coal, the longer it's been in the earth, the more it's transformed from the original plant material. So picture way back when the earth was very rich in carbon dioxide and oxygen, wasn't much animal life at all, and we have uh, many areas of the earth covered with lush ferns. And when those ferns fell to the ground and were ultimately covered by soil and buried deep within the earth, that's what initially caused the coal deposits. The natural gas and the petroleum are usually found together. Those result not from plant life decaying over time, but from animal life decaying over time. And what we mean by animal life is, not dinosaurs and mammals, but more like algae and microorganisms that existed mostly in the ocean. Then those microorganisms were buried over time. They're rich in carbon and hydrocarbons. When they were buried deep within the earth, they slowly have transformed into this natural resource, which is liquid petroleum and the associated gas on top of it called natural gas. Okay, and so natural gas is mostly methane. Okay, so in terms of resource terminology, we'll go through this pretty quickly. It's not critical. I like the graph on the next page better. But we're going to define um, these resources based on how easy they are to find within the earth. Okay, so if we go sort of, we're a geologist and we're hunting in the earth and we're looking for, let's say, petroleum. We're a petroleum engineer. If they're very easy to find, then those are going to be proven reserves of these fossil fuels. Okay. If we're not sure that they're there, they're in a brand new oiled field that we're just discovering there may be some oil in. Well, those are sort of going to be unproven reserves. So we're going to have to do some research and do some test wells to determine, is there really oil where we suspect it is? So we're not 100% sure. So the proven stuff is the stuff that we're sure about, and the unproven stuff is the indicated reserves down here, and those are the ones that we know how to get it out of the earth, but we're not 100% sure that if we go digging, that it's really going to be where we think it is. So I'm going to read these through again. So the proven reserves are reasonably certain to be produced from known reserves under existing economic conditions and technical under existing economic and technical conditions. Okay, so that means we can get them out of the earth at a reasonable cost. That's the economic condition. And we have the technology available. So the proven reserves, I want you to think of as coal fields in Wyoming that we're sure that they're there, coal fields buried in Pennsylvania that we're sure that they're there, or oil fields in Texas, Alaska, and the Gulf of Mexico that we've drilled hundreds of wells in those areas, and we're pretty sure that when we drill, we're going to find oil. Okay, so those are the most certain ones. The indicator reserves are believed recoverable from known fields using improved technology. Okay, so this would be stuff like um, fracking or trying to get the petroleum from something like the tar sands. So we know where this material is, right? The southern tier of New York State, like underneath the cities of Binghamton and Ithaca, and between sort of New York State and Pennsylvania. So the top of Pennsylvania and the bottom of New York State going west, there are known reservoirs of um, material that have natural gas in them. But that natural gas is not in a traditional form of like a bubble of natural gas. It's basically soaked into the shale rock that's there. So the only way to get it out is a technique called fracking. So fracking is an expensive way to get the natural gas out. As the technology becomes better, that kind of reserve will move from a proven, from an indicative um, reserve to a proven reserve. But right now, since it's a little bit too expensive to get out of the ground, we don't take that much of it out because the technology isn't good enough and the economics don't make it worthwhile. Remember, the oil or the gas is going to stay in the earth until it's profitable for somebody to take it out of the earth. Okay. So indicated reserves are believed recoverable from known fields using improved techniques. The last kind are called inferred reserves, and inferred reserves are those deposits expected in identified fields but not yet measured. Okay, so this graph, which comes from the old textbook, is pretty helpful. Okay, so what you have here is in the upper left-hand corner, you have the most traditional kinds of oil fields that exist, and we're sure. So let's do an oil example versus a coal example. So we know they exist, and we know how to get them out of the ground, and we can get them out of the ground at a cost that the companies can make a profit. So we're extracting this natural resource all the time. So what kinds of places am I talking about? I'm talking about the oil that exists in Texas, Alaska, the Gulf of Mexico, Venezuela, Saudi Arabia, the United Arab Emirates, all of these places that are currently pulling oil and gas out of the earth at a profit. So this is the kinds of things that are going on. Another really important oil and gas field is in the North Atlantic, right off of the coast of Norway and Sweden. We've discovered a lot of oil in the last 25 years. So those countries are extracting the oil and making a profit right now. So you don't think of Norway as an oil producing nation, but it is. So that's the most traditional stuff. Okay, so let's go across the graph this way. And so this is uncertainty. So if I'm certain that there's oil off the coast of Norway, there may be other areas in the earth that later on that we suspect there may be oil in, maybe in Central Africa that we don't know about yet. So we'd have to drill test wells to see if oil really exists in those places. Okay, so again, same technology, traditional pumping oil out of the ground, but we're not sure in those geographic locations if it really is there or not. So reserves are stuff we're sure about, resources are stuff we're unsure about. Okay, so what happens when you go down this way? Well, when you go down this way, we know that those materials are there, but they are more expensive to get out of the ground. So we don't tend to extract them from the earth until the price of gasoline goes high enough to make it worthwhile. So what would be down here? Maybe fracking would be here. The coal sands in Canada would be here. We know there's hundreds of miles of this coal sands that exist in Western Canada. They're right in front of us. They're on the surface of the earth, but yet it's very expensive to transform the coal sand into something useful, to make a barrel of oil out of, a big pile of basically oily sand is very expensive. Okay, all right. What's down in this corner here? The type that we probably will never go to. Those are the kinds of resources that are very expensive to get out of the ground. They take a lot of energy to extract them and then to refine them. And we're also not sure if they're really there, right? We haven't seen for certain that they're there. So we're probably never going to get down to here. Okay? As gasoline prices go down, this box gets smaller and people take energy from only up in this top section here. As gasoline prices go up, people start to move further to the right. The companies, I guess, not people, and they also move down. So these little stars here indicate where it makes sense under good economic conditions when gasoline prices are high for the companies to do extracting in those kinds of spaces, right? When the prices go down, everybody goes back to the easiest, cheapest stuff to get out of the ground. Okay, hope that makes sense. Okay, so let's talk about petroleum first. Okay, so petroleum, which we call oil, is hundreds of hydrocarbons all mixed together. Okay, if I showed you a diagram of what's in your gasoline, it just in your gasoline is 50, 60, 70 different chemical compounds. So the raw crude oil that your gasoline was extracted from even has a bigger mixture of more chemical compounds. What do they have in common? They're all hydrocarbons. They're chemical compounds that have mostly hydrogens and carbons in them. Okay, an example of that, a representative hydrocarbon that's an important component of gasoline, and if it's in gasoline, it must also be in the petroleum that they extracted the gasoline from, is called isooctane. So the reason why it's called octane is because it's an 8-carbon hydrocarbon. So the oct comes from the C8 part. And then there's 18 hydrogens around the carbons in this fashion. The reason why they call it isooctane is because 3 of the carbons, this one, and this one, are not along the straight chain of carbons. If this was linear um, octane, okay, or they call it N-octane, straight chain octane, instead of it being 1, 2, 3, 4, 5 in a row with 3 hanging off to make it 8, it would just be 8 in a row, with each one of them having a hydrogen on each side, so it'd have a long, slender compound. But that's not the compound that's so critical to gasoline. So since isooctane is burns very well in internal combustion engines, we use it to rate the gasoline. So the higher the percentage of isooctane that is in your gasoline, the better the gasoline will burn. Okay, so you pay more for that. Okay, so uh, that's the particular chemical compound. The other thing that you might notice is that all of the bonds happen to be single bonds in this chemical compound. Okay, if I drew out one of these CH3 groups over here, right, and I expanded it, so I showed you this part over here, right, and then instead of just writing CH3, what does that really look like? It looks like a C, each one again with one individual H. So this is the drawn out version of that CH3. So you really have one of these guys here, here, and here. Okay, so it's kind of like a bulky molecule. Again, what's special about it? It burns very well. It burns very cleanly. Okay, so you guys are going to be responsible for writing balanced chemical equations just for hydrocarbon combustion. Okay, so the definition of the complete combustion of a chemical compound is the reaction of the food or the fuel, in this case, um, the isooctane, with oxygen, with O2, to produce as the only 2 products carbon dioxide, water, and energy. Again, the definition of complete combustion is the reaction of the hydrocarbon with oxygen to produce carbon dioxide, water, and energy. How does the energy come out? In the form of heat. So if I asked you to balance this chemical equation, How would you go about doing that? We practiced this a little bit in class, but I'll do it again. So in other words, where does this 2 and the 25 and the 16 and the 18 come from? So let's go through that. I'll rewrite it. CH18 plus O2 goes to make CO2 and H2O. Okay, so that's the complete combustion. Okay, these two are always going to be in the gas form because your internal combustion engine has a fuel injector at each of the pistons, so it squirts a vapor of the liquid gasoline into this hot chamber, so it immediately forms a gas. It also pulls in oxygen from the outside air, right? So it pulls air in, and the oxygen in the air reacts with the fuel in explosions that occur every time the piston goes through the power stroke to create the exhaust, which is carbon dioxide and water. Okay, all of them in the gas phase. Okay, so let's practice balancing this. So one of the things that I told you whenever you balance a combustion reaction, always do carbon first, hydrogen second, and oxygen third. It'll turn out to be a lot easier that way. Okay, so here we go. If there's 8 carbons over here, there's no carbons in the water, there's no carbons in the oxygen. That means all the carbon from the hydrocarbon winds up in carbon dioxide. So this 8 means that you're going to need to form 8 carbon dioxides. Okay, now it may turn out that we have to double that later on, but for right now, this 8 balances with this 8. 8 times 1, 1 times 8. Okay, next, let's do hydrogen. This is an 18. This is just a 2. All of the hydrogens that come from the hydrocarbon wind up in water. So if this is 18, I'm going to need 9 over here because 9 times 2 is equal to 18. So now my carbons are balanced and my hydrogens are balanced. 1 times 18, 9 times 2. Okay, last, oxygen. Why do we save oxygen for last? Because it's a mess. There's some over here, there's some over here. So we're going to count them up on this side and make it right with the oxygens over here. So start on this side. I have 8 times 2 gives me 16 oxygens here. Okay. Plus 9 times 1. There's a 1 over here. I can't see it, but if nobody writes anything underneath it, it means 1. So 9 times 1 gives you 9. So 16 and 9 gives me 25. Well, if I have 25 O's over here, right? I counted up the individual O's. That means I need 25 O's over here. Huh, well, I have a problem, right? How do I get 25 when I'm stuck with twins? I'm stuck with sets of 2's. So in order to get rid of that problem, when you have an odd number of oxygens here, go back to your whole reaction and double everything except for the oxygen. Just leave that alone because we'll fix that at the end. Double the other 3 guys, and my 25 problem will go away because if I double everything, 25 will go to 50, and 50 is an even number. And if I have 50 and I have to break them up into sets of 2, that's just going to be 25 times 2 to give you 50. Okay, so let's double everything, right? This is not going to be 1 anymore. I'm going to change it to 2. This is not going to be 8 anymore. I'm going to change it to 16. This is not going to be 9. I'm going to change it to 18. So I've doubled everything. Okay. Now, let's assume that we were right, and then we'll count them up later to make sure, right? Before I doubled, I had 25 O's, so now I must have 50. That means I need 25 times 2 to give me 50 O's on this side. So when this is completely balanced, there's going to be a 2 here, a 25 here, a 16 here, and an 18 there. Okay, let me rewrite that. Nice and neat, all balanced. And let's double check everything. Right? The total number of each type of atom on the left has to equal the total number on the right. Let's do carbon again. How many carbons over here? 2 times 8 is 16. How many over on the other side? 16 times 1 gives me 16. So the carbons are set. Let's do hydrogen.
Okay, all the hydrogens on the left are over here. There's none over here. 2 times 18 gives me 36. How about the other side? None over here. 18 times 2 gives me 36. So the hydrogens are balanced. Let's do O, right, for oxygen. I'm just writing the X here so that you don't think it's the a 0, okay? So, good. You know what? You can just put an O here. What I'll do is anytime I have a 0, I will put a line through it. Okay, so that's oxygen. Okay, no oxygens here. 25 times 2 gives me 50. Okay, how about on the other side? 16 times 2 gives me 32 plus 18 times 1. That also gives me 50. So this is completely balanced. So that's what I'm going to ask you to do. So in review, you are to know that the reaction, the complete combustion reaction, means the reaction of whatever fuel or food that I give you. I could give you citric acid and say it's combusted in the body. I can give you a starch. I just have to tell you what the chemical formula is. Or I can give you a fuel like methane or isooctane. So the food or the fuel that I tell you about, you have to memorize that complete combustion means the reaction of that food or fuel with O2 to produce carbon dioxide and water and heat, and then know how to balance it. I'm going to ask you to do that on the next test. Okay, good. Okay, so top of the next page. There's the balanced chemical equation. Let me show you something called the energy profile for this reaction. Kind of reminds me of the potential energy diagrams we did at the very beginning of the semester for physical systems, like when we threw a ball up in the air, or someone rode a bicycle or climbed a ladder. What did they do? They gained energy and they stored that energy by going uphill. Well, for us, our potential isn't going to be physical potential energy, it's going to be chemical potential energy. When we make these hydrocarbon molecules, in a sense, we make unstable molecules that are very reactive. They kind of have fledgling weak bonds. These carbon-hydrogen bonds aren't very strong. This oxygen-oxygen bond isn't very strong. This is a very reactive molecule. Both of these things want to react. And guess what? You put them together and you put a spark, they will react explosively. So the energy profile for all of the combustion reactions, okay, for all the combustion reactions is going to be downhill, right? And it has a delta H, which is called the enthalpy of the reaction or the heat of the reaction. That's negative. Why? Because we give up potential energy. We have more of it in the beginning, and after we have less, right? If I assign this a number, and this number was 10, and I assign this number over here of its starting place, and this number was 90, I would take the final number minus the initial number, and now it would give me delta H. Delta H is always the change in H. So 10 minus 90 is negative 80. Anytime you go downhill, you should expect delta H to be negative. We call that exothermic. Delta H is exothermic. That's the downhill part. So what part was I ignoring? I was ignoring the little hill in between. Even a reaction like this that wants to happen needs a spark, needs a little bit of energy to get it going, right? Gasoline, in the absence of oxygen and a spark, isn't going to react on its own. Okay, you have to really heat it up a lot for that to happen. But if you provide a little bit of seed energy to get it going and just get it up and over this hill, then the rest of it will take over. Okay, so that initial amount of energy is called the energy of activation. It's always positive, and it's measured from the starting point, this number over here, the 90, okay, up to the highest point. So maybe it finishes up at 100. It's always uphill, it's always positive because from here to here, 100 minus 10 is going to be positive, 100 minus 90 is going to be positive 10. So I was just making up those numbers as a reference, right? I don't expect you to know the numbers or do the calculation. I just want you to get the trend, right? That there's always going to be a little hill that I have to get up and over, but the net difference between the starting point and the final point is downhill. So we're graphing here the chemical potential energy versus time. This is before the reaction happens. This is after the reaction happens. And what's the other product that would come out? We would also generate a lot of heat, right? And that heat is what we use to heat our homes or to generate power for our car. Okay, so very bottom of the page, delta H is equal to minus, it's a negative, it's exothermic, gives off heat. Okay, you don't have to worry about delta S. I'm going to skip that um, for this course. Okay, so don't worry about what delta S means. Second thing that you do need to know though is that the energy of activation is always going to be positive. You need to get up over a hill. So I think I have a couple of examples for you in the next one. Again, responsible, you're responsible for the change in enthalpy or the change in heat, right? And that's going to be exothermic in all of these reactions. Okay. Here's our definition of complete combustion. It's the reaction of a food or a fuel with oxygen gas to produce carbon dioxide and water vapor as the only two products. If I asked you about the complete combustion of the simplest hydrocarbon, methane, right? Methane is just one carbon with four hydrogens around the outside of it like that. That's natural gas. Very simple molecule. How would we write that in a condensed form? CH4. Okay. So the complete combustion of methane means that methane reacts with oxygen to produce carbon dioxide and water. Okay, so let's balance it. And I'm going to just balance it up here, and then we'll go down and you can go over the steps yourself when you read the notes. Okay, first, we're going to do C followed by H followed by O. So one carbon here, leave it alone. No reason to change something if it's already balanced. The number of carbons in the hydrocarbon are going to turn out to be equal to the number of carbon dioxides that you make. So we're at 1 and 1. All right. How many H's? There's 4 H's here, but there's only 2 over here. So I have a feeling that I'm going to wind up having to multiply this by 2. Now I have 4 H's here, and I have 4 H's here. Okay, let's count up the total oxygens on the right-hand side, and then fix the right-hand side with the left-hand side. See, oxygen should be saved for last because it's only in one place on the left-hand side. So when I change this, it's not going to mess this guy up. So start over here. I've got 1 times 2 is 2. There's 2 O's over here. Plus 2 times 1 is another 2. So there's 4 total O's on the whole right-hand side. Guys, this 2 has got nothing to do with that oxygen. Each water has 2 hydrogens and 1 oxygen. So there's just 2 O's here and 2 O's here. See if you see that. So I got a grand total of 4 over here. I need 4 over here. I've only got 2. How can I get this to 4 O's? 2 times 2O, 2 times O2 gives me 4 oxygens. So that's the way this thing is going to be balanced, and you'll see that at the end. Okay, you're going to need a 2 on the oxygen and a 2 on the water. Okay, so here's the end. And that's what we had. That's the complete balanced chemical reaction of for the combustion of methane to produce carbon dioxide and water. Here's the energy profile. Just like we said, combustion is always exothermic. The hydrocarbon and the oxygen are reactive molecules. They're high up in energy, right? They're high up in energy. They have stored up energy. The carbon dioxide and the water are very stable molecules. They're low down on the scale. They're so low on the scale that we actually use them to put fires out, right? We douse fires with water, or we use um, uh, fire extinguishers that have carbon dioxide in them because don't support combustion, right? So you're basically drowning out the fire by blowing carbon dioxide gas at it or water at it. They can't burn, they're already burnt, right? They're the products of combustion. They don't burn any further, right? So they're very stable. These are the reactive ones. So two things you should notice. Delta H is downhill. This would be an exothermic reaction, give off energy. And energy of activation, you always have to climb up over a little hill. Even though methane is very dangerous in your house, you're very worried about having an explosion. The explosion won't happen without a spark. Okay, so you have to be very careful if somebody leaves the gas on that no one comes in, right? And first you open the windows and aerate the house totally before anybody lights a match or anything like that. That's when the explosion will occur. Good. So let's read this note down at the bottom here. Delta H is called the enthalpy. It's just a fancy word for heat of the reaction. The net difference, it's the net difference between the energy of the products and the energy of the reactants. Delta H is H of the products, which are very low, right? They have a low potential, not very much stored up chemical energy. You take the products minus the potential of the reactants. The reactants are unstable, high up in energy, just like lifting something up, it's unstable. The products minus the reactants is always going to be negative because it's a downhill reaction for combustion. Okay, so what is H? H is the enthalpy of the products minus the enthalpy of the reactants. It's going to be downhill in all combustion reactions. Here's the definition of energy of activation. We call it capital E act, act for activation. It's the amount of energy needed to get the reaction going, the difference in energy between the reactants and the highest point on the pathway. So you basically draw an arrow from the height of the initial place, right? So just work your way over to here, go straight up. How much is the top of the hill? So if you were hiking, delta H would be from your start of your hike to the top of the mountain. Okay. If you finished up your hike over on this side and you took a little tram back, right? Your overall distance in height, delta H, would be from here to here, right? This is where maybe you camped out or something one night. Delta H is just the starting point to the highest point, not delta H, sorry, energy of activation. This would be delta H. This particular reaction here is endothermic. It goes uphill. But notice it still has a hump that you have to get over, right? When you wind up at the products have some stability. So this kind of reaction would be the opposite of combustion. This would be something like photosynthesis, which we're going to see next, the creation of the hydrocarbon material from oxygen um, and carbon dioxide. Okay. All right. So here's some problems for you to do. I'll let you work on these on your own. Write the balanced chemical equation for the complete combustion of the following. This is alcohol, right? This is what's in drinking alcohol. It's ethanol. Well, ethanol burns, okay? Our gasoline is supplemented with someplace between 5 and 15% ethanol. That's because in the United States we grow a lot of corn, so the ethanol from the corn, not all the corn goes into food, some of it goes into fuel. So probably for the last 25 or 30 years, we've been basically subsidizing the farmers in the Midwest to grow ethanol to go into our fuel stock. So we mix it with the gasoline. This way we use less fossil fuels than we ordinarily would. So from that point of view, it's a net positive. Okay, there's other questions. Is it environmentally practical because it takes a fair amount of energy and water to grow the corn. And if we're just going to use the corn for energy, maybe that's not the most efficient use of corn. It may actually take more energy to make a gallon of ethanol out. You might have to use more fossil fuels with all the tractors and the pumping of the water and everything. So it's an open question, but right now we're still doing it. If you hear about a car that's a flex fuel, that vehicle can use higher percentages of ethanol, right? It may even be able to use 50% or 100% ethanol in place of the gasoline altogether. So that's ethanol. Okay, here's isooctane. We already balanced that, but you can practice it again. Here's sucrose, right? So before I was talking about foods or fuels. So you can burn the sucrose, you can burn sugars, and that's what your body does. Your body in goes undergoes cellular respiration. Well, cellular respiration, the net products are just carbon dioxide and water. So burning sugar in your body is identical to burning sugar on the outside. It's just a slower process, and your body extracts the energy and uses it for to move your muscles. Okay. And benzene is a component of gasoline. It is a little six-membered ring where there's a carbon at each one of these junctures and one hydrogen hanging off. They don't draw them in the picture, but that's where the six hydrogens are. There's one there, one there, one there, one there, one there, and one there. So there's the six hydrogens, and each of these corners is the six carbons. So it's kind of like a chain link fence that works its way around. Okay, so that's a component of gasoline. It's a toxic component of gasoline, so we have to be careful. When gasoline spills, that's one of the things that we're worried goes into the soil. Some of the other components are not as dangerous. Here's two more. Top of the next page. So each one of these, you're going to write the balanced chemical equation for. Styrene, like you have heard of styrene, you make polystyrene out of it. Styrene is the monomer that you polymerize into polystyrene, which is styrofoam. Okay, so it's C8H8. If you could burn it completely, it would make just carbon dioxide and water. The problem is if you took some styrofoam and you started to burn it, it probably wouldn't burn completely and you'd get a lot of noxious gases, which are intermediate products, not completely finished the chemical reaction that would go off into the environment. And those things are the pollutants. The carbon dioxide and the water are not the bad ones. And here's toluene. Toluene is a solvent. That's also a gasoline component. You know the smell of toluene from airplane glue. Airplane glue is dissolved in toluene. Toluene is, again, six-membered ring. There's six carbons there. Then there's one guy hanging off to make a total of seven. So this C7 comes from one, two, three, four, five, six, plus one is seven. And where does this eight H's come from? There's three here. Then there's one at each of these corners. Three, four, five, six, seven, eight. The styrene here, C8H8. Here's your one, two, three, four, five, six, seven, eight carbons. And where's your eight hydrogens? One, two, three, four, five, six, seven, eight. They just don't draw them at the corner here. Okay, so your job is for those five compounds to write the balanced chemical equation for their combustion. Okay, here's another problem, and I'm going to do this one on a piece of paper for you. It is sketch the energy profile for the combustion of toluene if delta H for the reaction is negative 3910 kilojoules per mole and the energy of activation is 420. Okay, so let's do this on a separate piece of paper. This would make a great test question. Okay, so the first thing that you realize is when someone asks you to sketch the energy profile, you make a box like this, and on this side, you have potential energy, the chemical potential energy, the stored up energy. And down here, you have time. So to the left, here's time zero. This is the beginning. This is before the chemical reaction occurs. Then something happens, and then you have after the reaction is over. Okay, so let's do the delta H part first. Here's our reactants. They have this much energy. I know to draw. Now, again, I'm just sketching this. So all I need to get is I need to get the heights, the relative heights correct. I don't have to get the exact number right. Okay, so I draw this one up high because the hydrocarbon has a lot of stored up energy in it. And then I say it's going to give off 3910, right? So it's definitely a downhill process, so maybe I'll draw that down here. So from here to here is about 4,000 kilojoules per mole. So each one of these lines could be about uh, maybe 750, okay? And that's how I would get to that 4,000, okay? Or actually, more like if I have to get to 4,000, it'd be about 1,500 each. So, right, so 1,500, 3,000, 4,000. Okay, so that's the difference from here to here. That's called delta H, okay? And delta H is going to be negative 3910 downhill, okay? All right, I can write the reactants here and here. So this is the toluene here. So I write C7H8 and it reacts with oxygen here. And the products are carbon dioxide and water. So you need to do that. Okay. How am I going to represent the energy of activation? The energy of activation is always positive. Even something like toluene takes energy to get it going. Well, this was about 4,000 going down, right? 3910 kJs for each mole. So I want to represent this about the tenth of the size of that because this is 4,000. So this is 400. So maybe I'll do something like that. Okay. And now this little bump here is the energy of activation. It's uphill and it's equal to 420. Okay, so based on these numbers that they gave me, I make this one about 1/10 the size of that one. Okay, now I'm not going to, measure them or anything like that, but you can't make this one huge, right? Because relative to this is going down 4,000. This hill is going up 400. That's about a tenth the size of that. Okay. All right, last topic. What's the opposite of combustion? How do things originally form? How do these foods or fuels originally form? Well, they form from a process called photosynthesis. So photosynthesis is conducted by green plant materials and some algae as well. So there are some animals that algae is not considered a plant, it's considered an animal that can undergo photosynthesis. So it's the reaction of carbon dioxide gas with water in the presence of sunlight to produce organic molecules, in this case, glucose. Okay, so that's just one example. And glucose is C6H12O6. It's the food or the fuel. You're making it this time instead of burning it up. And the other byproduct of photosynthesis is a good thing. It's oxygen. So where do we get the oxygen that we breathe? It pretty much all came from photosynthesis going on in the earth. And we're very, very lucky that at this stage of the Earth's life, we've got 20% oxygen in the atmosphere. So photosynthesis has been blowing away combustion for I shouldn't say billions, but hundreds of millions of years to the point that we have an oxygen-rich atmosphere. That's unusual. None of the other planets have oxygen-rich atmosphere because they don't have photosynthesis going on. Okay, so carbon dioxide and water are very low in energy, right? They're very stable, strong molecules that don't react. So they are down here. I put energy into them. I have to get up over this hill. Where does that energy come from? That energy comes from the light, right? Photosynthesis only happens in the presence of light. So the plant material, right, which is where the photosynthesis is going on, the plants extract the energy from the sunlight and use it in a series of chemical reactions to build up this very special molecule, glucose and oxygen, out of these inert, unreactive species, carbon dioxide and water. Okay? If you balance it, you can balance this the same way that you would have balanced the combustion of it. Do carbon first, hydrogen second, and oxygen third. So this is the complete balanced equation. Notice it's the opposite, the exact opposite of combustion. So photosynthesis is the reaction of carbon dioxide and water in the presence of light to make organic matter, in this case glucose, and which is a sugar, and oxygen. Okay, and notice delta H is uphill, positive. So if I was going to give you the numbers associated with this, I would say that delta H would be something like positive 1100 kilojoules per mole. And the energy of activation, now look at this, the energy of activation, which is always the energy from the starting point to the higher point, is going to actually be bigger than delta H in this case. So the energy of activation here might be something like positive 1500 kilojoules per mole. Okay, energy of activation is always draw a line from wherever you start, go to the top of the mountain. Okay, so you get up over the mountain and then you rest up here. Okay, this is an endothermic process. Photosynthesis is endothermic, combustion is exothermic. Okay, that's it. That's the first half of the fossil fuel chapters. We'll see you on part 2.